In this presentation, we're going to talk about seismic design of beam column joint in reinforced concrete structures. Based on ACI 318 and ACI 352, which are recommendations for design beam column connections in concrete structures, these two standards or manuals define a beam column joint as that portion of the column within the beam and slab that frames into the column. The connection the connections enable forces and moments to be transmitted among the beams and columns. Um, in many buildings, joint design requirements will control the sizes and reinforcement of the adjacent frame members as beams and columns. This photo shows the damage in a building by an earthquake and the importance of transverse reinforcement for the column and for the joint. Um, the importance of beam column joint. Um, these joints guarantee the overall stability of the column, since its failure usually generates the beginning of a progressive collapse mechanism. In earthquake-resisting frames, a primary design goal is for joints to remain essentially elastic while plastic hinges form in adjacent framing members. Framing action can result in relatively large shear forces being transferred across the joint. The value of the shear in the column is maximum. As we can see in this can be seen in the diagrams when we design the columns. It is the area where the steel of the beam must develop its maximum effort to withstand the negative moments of the support. That's the bond deterioration of the longitudinal reinforcement in cyclic loads, like earthquakes. And they present an inversion of moments during earthquakes. Lateral loads produce moments that must be transferred between beams and columns at all joints. As we will be demonstrated subsequently, this moment transfer can produce very high shear stresses in beam column joints, as we can see in the next slides. As we can see in the image, this is a good failure mechanism where the hinges form in the beams. Joint reinforcement generally comprises horizontal transverse reinforcement in the form of hooks and cross ties, plus distributed column longitudinal reinforcement. This figure shows an example of an interior connection with joint reinforcement that may be suitable for earthquake resistance. Um, Joint classification generally refers to these joints as interior, exterior, T, and corner connection, as you can see in this image. The second classification is that the reforming serves many roles, including confinement. Uh, uh, well, in this is basically two types. The first type um, is those that resist loading without significant inelastic deformation, and type 2 connection that is this this one that sustained deformation reversals into the elastic range as in earthquakes. And in the other classification is that in regions of high seismicity, beam column joints in modern seismic force resistant system are designed with transverse lateral reinforcement and well-distributed column vertical reinforcement that in contrast in regions with a low seismicity we don't need sometimes this reinforcement. On the next couple slides, we're going to check an internal joint being based on the ACI 352 procedure. Um, from the design, we have the column design and also the beam north-south and east-west design. We have the slab design and the materials characteristics. The first check is the transverse reinforcement required for its good performance in the structure, as we saw in the first slide in the earthquake. Um, so we find the area of the stirrups. Then we find spacing that could govern the reinforcement, where the BC, remember that is 20 inches and the diameter of the bar is number 9. Or we have another limitation that is 6. In this case, the governed value is 5. And we have some limits here. The total area in each direction of the hook should be at least equal to this expression, but should not be less than this other expression, where this BC is the confinement B in this case. And then we have this ACH that is this governed value, because this is the upper limit, that is 1/6, but because it's an internal joint, we have to reduce by a half. So 0.8 is equal to that the one we have 0.8. So we check this. Then we have the probable moment to find the shear of the column. The probable moment is the tensile force of the steel in the left or right, and that is this, and the second expression is this distance of this steel. In this case, this alpha is the post fluency of the steel that is 125. We know how to find the expression A, and we have to find it for positive bending moment and negative bending moment. Then we have the joint shear. The the shear forces in the joint are, in this case, we have to find an effective area that we can use in the expression, and we have to check in here. So to find this effective area, we have that is the slab participation under negative bending, that are these taut fibers in tension. We have that the first requirement is the 1/4 of the span length of the beam. The width, the second one is the width plus 8 times the slab thickness on each side. And the third one is the wet width plus 1/2 the clear distance to the next web on each side. That govern the less. And um, and we have that the check is that the effective width is less of 2 times of the B from the beam. Then the shear forces in the joint are in this diagram, where we can see the shear from the column, the shear of the column, the shear from the steel, in compression and in tension, and the shear V sub U. We have first we find the shear in the column with this expression, and then we find the VU, which is the summation of forces, and we also use the post fluency 125. Then the expression that we use for V sub n is this one, and this value is based on the physical characteristics of the joint, where they effectively confine on all 4 vertical faces is 20. So in this case it's 20. Because in this case we have the B sub A H sub J, that we have these 3 values. It has to less of these values, the B of the column plus the B of the beam over 2, B of the beam plus this M times the H of the column over 2. In this case, because the eccentricity between the beam center line and the column center exceeds B of the column over 8, we have that this M is 0.5, but 20 that is the B of the column over 2 is 5, but is less than the extension of the column beyond the edge of the beam. So in this case we use the extension of the column beyond the edge of the beam, that is 2 inches. Finally, we compare the demand and the capacity of the joint, and we check. In this case, we check the value. And we have another 2 requirements. That is the flexural strength ratio. That is the ratio of the moment in columns over the moment of the beam, and is need to be high of 1.2. So we check that. And the other one is the beam and column bars passing through the joints, and we have the check of the ratio, but in this case we check the age of the column, the age. So we have the F sub y, that is the same in this case 60. Finally we check for the column and for the beam. Thank you to hear my presentation.